Now we'll study the classification of magnetic substances. First of all, you could classify entire group into two parts, that is weak and strong. When we talk about weak magnetic substances, we are concerned with dia and paramagnetic substances. Strong magnetic substances, you have three categories, that is ferro, antiferro, and ferrimagnetic. First of all, we'll study about diamagnetic substances. You see, this property is considered as universal. This property basically arises because of the paired orbital. Basically, no atom of diamagnetic substance is a magnet. But whenever you place this substance into external magnetic field, because of the Lenz's law, the orbital that is responsible for opposite field becomes stronger, and you could say that this substance is magnetized opposite to the external field. The magnetic lines are always rarer, rarer in these substances. The diamagnetic substance will always have a tendency to be perpendicular to the external magnetic field. These will always be repelled by external magnet, as shown over here. You see, if you place the magnetic poles near this mouth of U tube, the substance that is of diamagnetic nature will be repelled from it. These are magnetized opposite to the field. Susceptibility is going to be negative. Value is round about 10 to the power minus 5, but that's a negative. Magnetic lines of force are rarer. You might say these have a tendency to have no magnetic lines of force. These rotate in magnetic field till the longest axis become perpendicular. Diamagnetic gases will always spread perpendicular to the external field. Solid, liquid or gas all can behave like a diamagnetic substance. The susceptibility is independent of temperature. Here, susceptibility is negative. That means if you plot the graph between I and H0, it is going to be a straight line, but on the negative side. In variable field, you see, the diamagnetic substance always will move from a stronger to weaker section of the field. Now, how to decide which field is weaker or stronger? You see, if the magnetic poles are at distance, then lines of force will have a possibility of leaking through. And within the middle point, within the two poles, is going to be the place of weaker field. But if the two poles are very close to each other, like north and south, you see, when I am drawing north and south poles separately, it doesn't mean that poles are existing separately. We are not concerned with another south pole. That's why I have avoided here another south pole. Similarly, I have avoided the north pole associated with the south. So, whenever north and south poles are drawn separately, you have to consider that we are considering the effect of these two poles only, although other component pairs are complementary pairs are there with these poles. When the poles are very close, the lines won't leak through. So, the point in the middle is going to have the region, you might say, of maximum field. This would be the point of maximum field, and if the poles are at a distance, this is going to be the point of minimum field. So, that I have shown over here by keeping the two poles at distance. When at distance, the point in the middle is weaker. So, strong to weak, the diamagnetic substance has concentrated. That's why you see one collection over here. And when the poles are nearer, the field is closer or stronger between them. And in that case, the field will be weaker near the pole. That's why near the pole you find the collection, and in the middle you see that the collection of diamagnetic substance is not considerable. The examples: water, alcohol, air, lead, antimony, bismuth, molecular hydrogen, mercury. This is the example for diamagnetic substances. One more thing, you see, if you go on decreasing the temperature of metals, superconductivity is exhibited by the metal. Interesting is that when it exhibits the property of superconductivity, at the same very time, diamagnetism is also very strongly developed in it. And a superconductor, when placed in external field, superconductor doesn't allow any magnetic lines of force to pass through it. This effect is called Misner effect. That means within the magnetic field, the superconductor placed will not be affected by the magnetic field. In fact, you could say that this expels all the magnetic lines of force from it.